All right, our topic for today here in section 8.7 is the unit circle. You might have heard this phrase before. It is a concept that looms large in your pre-calculus class, for instance, and it has somewhat of a bad reputation there as this really complex object in mathematics and higher mathematics. I'm about to demystify that. And the reason I do this, you'll need a little bit of background here. Okay, so the mathematics that we do, the geometry that we do, is primarily ancient Greek mathematics. If we were to bring Euclid forward in time, and if you were to say no English, I think you would almost immediately recognize everything that we've done in this class. All that would really come as a surprise to him would be our protractor and ruler postulates, which make use of the real number system, and the Greeks didn't have the real number system in the form that we do. But I think that could be taught relatively easily to Euclid or to some ancient Greek mathematician. And then everything that we've done in this class would be familiar, would be immediately familiar. Okay. However, in this context, the context of our study of trigonometry, I think it extraordinarily useful to update, to bring into modern time our definitions of the trigonometric functions of sine and cosine and tangent. Now, the payoff for this really won't come until section 8.8, where we learn how to use the trigonometric functions to solve for unknown sides and angles in non-right triangles. That might seem mysterious, but I'll demystify that in the next section. But just know that the reason we do this is it is extraordinarily useful. And this is why it is that modern mathematics doesn't make use of the ancient Greek definitions of sine and cosine and tangent. Do know, however, that the new definitions that I'm about to offer, ones in terms of this object called the unit circle, are not inconsistent with the Greek definitions. They merely extend them. Okay. Now, the ancient Greek definitions of sine and cosine and tangent assume that we're inside of a right triangle, and there we take the sine, cosine, or tangent of one of the acute angles in a right triangle. And then, of course, what we get back out is a ratio of sides in that right triangle. So for the ancient Greeks, it would make no sense to talk about, for instance, the sine of, 118 degrees. That just makes no sense at all. That cannot be an acute angle measure in a right triangle, so that simply cannot be done. However, the modern definitions will allow us to do that. Okay, and you might have suspected, if you spent much time with your calculator, that something was up with the trig functions that we had not discussed. So if you might try this right now, pull a calculator out, type in 118 degrees, take the sine of that. Your calculator won't give an error message. It will give you a value. Okay, and you might be surprised about what that is, or not. But it does. It gives you a value. Okay, so you might have suspected then, you should suspect, that something is up, right, with the way that we moderns do trig, that it must in some way be different from the way the ancients did this. Okay, and I'm about to show you the way in which it's different. But do keep in mind that it is fully consistent with the ancient Greek definitions for acute angle measures. Okay, so the modern definition of sine will give you a value, say, for the sine of 23 degrees, and the modern definitions will give you precisely the same value for the sine of 23 degrees. But the modern definitions will allow you to take the sine, cosine, and tangent of non-acute angles. Okay, so let's talk about how this is done, and the tool that we'll need for that is the unit circle. So I'll pop through this. We've already talked about it. So the story that we tell begins with the unit circle. Okay, and what is the unit circle? It is a circle of radius 1. That's what unit means in this context. Unit means circle of radius. Unit circle means circle of radius 1. Now here's what we do with that unit circle. We pass a pair of lines through its center point that are perpendicular to one another. And you see them in this diagram. So A is the center of our circle, and we have passed two lines, I've called them X and Y, through A, and X and Y are perpendicular, right? As is indicated in the diagram. Now, of course, given the work that you've done in your Algebra 1 class, and perhaps other classes as well, you probably suspect why I call these X and Y. But at this point in time, that's really of no significance. I just simply picked names for my two lines, and I called them X and Y. Okay. Now, next step in our story, we choose a point that I've called B on that unit circle. And then what we do is from B, we drop perpendiculars to both X and Y. The perpendicular to Y in this diagram is BD. The perpendicular to X is BC. And remember our language of foot of the perpendicular. When you drop a perpendicular from, say, a point to a line, the point at which that perpendicular terminates is called the foot of that perpendicular. So the feet of the perpendiculars in this diagram are C on X and D on Y. Okay, so that's the second part of our story. And then third part of the story is this, is we have created an angle. Well, of course, we've created multiple angles, but the angle that we care about is the angle formed by that portion of X that goes from A to the right, that ray, okay, that half line from A along X to the right, and AB. Okay, that's the angle that we care about. Wherever B happens to be, that's the angle that we'll consider. That's the angle that we'll use. And in my diagram and the other diagrams that we'll have, I call that alpha. That's what that symbol is that perhaps you do not recognize. That's the lowercase Greek letter alpha, and Greek letters from the first part of the Greek alphabet, alpha, beta, gamma, are often used for angle measures. So that's the angle that for us matters. Now, next part of the story. And this is where it really begins to differ from the story given to us by the ancient Greeks. As a matter of fact, everything we've said so far, the Greeks, of course, would perfectly understand. But now we need to introduce negatives, okay? The Greek number system had no negatives in it, didn't even have 0, and it didn't have negatives. But we're now about to have negatives. How do we get negatives? Well, recall that C was the foot of the perpendicular on X, and D was the foot of the perpendicular on Y. Now let's say that if C is to the left of A, then segment AC has negative length. And if D lies below A, then AD has negative length. That is, left and down are negative. Left on X is negative. Down on Y is negative. And right and up are positive. Okay, so that's how we introduce negative quantities into the story. Now, segments such as these, where we can have potentially negative values, and it depends upon which direction we go, these are called directed line segments. Okay, and we'll say that these can have negative length. Okay, these can have negative length, and this is the crucial way in which our modern story differs from the ancient Greek story. They wouldn't have the possibility of directed line segments. They wouldn't have had the possibility of negative length. So, just some examples of negative lengths. So notice that I've moved B around my circle. Okay, it was top right to begin with. Now it's like top left, okay, on the left-hand side here. Once again, we dropped the perpendiculars, BC to X and B to Y. Notice that now from A to C, that travels in the leftward direction, okay? So we will say that that is negative. So I'll put a negative symbol there, which is a terrible negative symbol. So how about a better one? So that's a negative from A to C because it's directed left. A up to D, well, it's up. That's still positive as it was before. And now consider what we have on the right. Okay, so in this case, B has been moved almost one complete rotation around our unit circle. And now as we go from A to D, we have gone down, so that's negative. And as we have gone from A to C, that's rightward, so that's positive. Okay. And you might think about this, about where our directed segments CA and AC and AD would be negative and positive. If it's in the upper right, then presumably it would be positive, positive. If it is upper left, and you might recall here, talk of quadrants, though we won't use that. And upper left, well, what would that be? So AC would be negative, positive. And then if we're in the bottom left, it would be negative, negative. And then finally, it would be positive, negative. So that should be clear enough. Let me make a distinction here. This is a usual distinction in mathematics. This will help us to stay clear about certain ideas in just a moment when we give our updated definitions of sine, cosine, and tangent. Let us distinguish distance from length. Okay, length is for us now a potentially negative quantity because it is directed length. Okay, and the direction gives its sign. If we're on X and we go to the right, we're positive, but if we go to the left, we're negative. If we're on Y, if we go up, we're positive, but if we go down, we're negative. Okay. But distance will always remain positive. Okay. So the distance associated with the line segment is the distance from one endpoint to another, and that will always be positive. And a nice way to state the relationship between them is that distance is always the absolute value of that directed line segment length. So for instance, if a directed line segment AB had length -1, then the distance from A to B is the absolute value of -1, which is just 1. Okay, so keep in mind this distinction. Distance will always be the positive measure, but length can be negative. Okay? Now, let's move on to our new definitions of sine, cosine, and tangent. They're still functions. Okay, we talked this function language before. That means that we have inputs and outputs. The inputs will still be angle measures, but the angle measures can now be non-acute. And what will the angle measures be? Well, it's that alpha from our diagram. Okay, that is, it is the angle formed with AB from center out to a point in the circle and the positive part of X. That is from A to the right on X. Okay, that will be the input. And the output will either be line segments or there'll be ratios of line segments. Okay, as you'll see. And here they are. Okay, here are the new definitions of sine and cosine and tangent. For some point B on the circle, which gives some angle alpha, okay, between AB and the positive part of X, the sine of alpha is AD. The cosine of alpha is AC. And the tangent of alpha is AD over AC. Okay, these are our new updated definitions. And notice that these are lengths of directed line segments. Okay, so they are potentially negative. For the example shown here in the diagram, both AD and AC would be positive, which means, of course, that AD over AC would also be positive, but, you know, they're potentially negative. Here's an example. You'll actually, on the homework assignment, work with a GeoGebra sketch that will allow you to read values off in the way that I've done here. So we have a measure of alpha, which again is between AB and the positive part of X, so 42.6 degrees. And AD in this case is 0.68 and AC is 0.74. And those, of course, we know must both be positive measures, okay? Sine, cosine, and tangent are lengths of directed line segments, and in this case, given the position of B, both of these are positive, so the sine is 0.68, the cosine is 0.74, and the tangent is the ratio of these, which is 0.68 to 0.74, which is 0.92. And notice that negatives are possible, as I have reiterated multiple times. So let's have an example of this. Now, in this diagram, what I've given you quite deliberately, and you'll do this sort of work on the homework assignment as well, the values given on the diagram are distances, okay? So that 0.76 and that 0.65, those are distances, okay? So they do not indicate the appropriate sign. We'll have to decide on that for ourselves. So let's see. Sine 139.34, okay, that's our alpha, the angle formed with AB and the positive part of X. Well, the sign is the directed length AD. But A to D is up, so the 0.65 should be positive, so we'll leave it just like that. The cosine of 139.34, well, let's see. That's by definition AC, but that is leftward directed, okay? So it's from A to C, which takes us to the left. That must be negative, okay? So the value of the cosine of 139.34 is the negative of the distance from A to C. So it's negative 0.76. And then the tangent is the ratio of AD to AC, which is 0.65 over negative 0.76, and a positive divided by a negative is a negative, so that's negative 0.86, okay? So there's an example of how it is to use the unit circle to evaluate trigonometric functions. And now let's talk a little bit about why it is that our new definitions are perfectly consistent and just extensions of the old definitions, okay? And what I mean to say is that if our alpha is acute, that is, if it is between 0 and 90 degrees, the old definitions and the new definitions completely agree. They exactly agree. So let's do that. For the case of sine, okay, the stories about cosine and tangent would be similar. I think if I can convince you in the case of sine, we'll be good. So notice that we have our unit circle again, okay? That is a circle of radius 1, okay? So AB is 1, that is indicated on the diagram. B is like upper right in our diagram. That means that alpha is acute. So this is something, for which the old definition should work. Now, the old definition tells us that the sine of alpha is BC over AB, okay? What is the old definition? That sine of an acute angle in a right triangle is the ratio of the opposite leg to the hypotenuse. Well, if I'm in right triangle ABC at angle alpha, acute angle alpha, the opposite is BC, and the hypotenuse is AB. So that's the old definition. But AB is 1, okay, and BC is AD. Let's reflect upon that for just a moment. Why would BC be equal to AD? Well, we know, of course, that we also have a right angle at D, and we know that X and Y are perpendicular to one another, so we have a right angle at A. And then ask yourself about this quadrilateral ACBD. It has 3 right angles. So what's the 4th angle? Of course, it's also a right angle. So what is this? It's a rectangle. And we know that rectangles are a variety of parallelogram, and parallelograms have equal opposite sides. So we know that BC and AD are equal to one another, okay? So again, old definition, sine alpha, BC over AB. But AB is equal to 1, and BC is equal to AD. So it follows that the sine of alpha just is AD, okay? And that is our new definition. The sine was the length of AD. So if A is acute, our old definition and our new definition completely agree. Okay, completely agree. And one could also tell this story for cosine and tangent as well. So let's make sure that we see this for the case of non-acute angles as well. Okay, why it is, let me pop back just a second. We still have right triangles implicit in the new definitions, okay? Now, the new definitions just simply talk about like the length of a segment when we drop those 2 perpendiculars to X and to Y, but there's still right triangles involved, okay? So let's make sure that we're clear about that, okay? So again, I'm only going to consider the sine of the angle. So notice in this case that I've allowed B to rotate around the circle significantly, right? So we're now bottom left, what you might have called it your Algebra 1 class quadrant 3. So this is between 180 and 270 degrees, okay? So again, our alpha is the angle formed with the positive part of X and AB, so there it is in the diagram. And what is the sine of alpha? Well, the sine of alpha is that directed length AD, but that's still a ratio in right triangles, okay? Because we do have the right triangle in this case ACB, okay? And we said that on the new definition, the sine is AD, but that AD is once again equal to BC, and we still have a right triangle, and it's still then a ratio of that BC to the hypotenuse, which has length 1. So there are still implicitly right triangles present, even though we don't explicitly talk about them in our definitions anymore. Now, final note, final thought before I finish up. You might have realized that what we have in effect done here is we've in effect constructed the coordinate plane, where of course every point in the coordinate plane has an x-coordinate and a y-coordinate, and these are sometimes positive, sometimes negative. Yes, as a matter of fact, that is in effect what we've done, okay? And if you do chapter 12, perhaps if we do chapter 12, perhaps we will, we'll take this further. We'll actually explicitly define what we mean by the coordinates of a point in a coordinate plane. But really, the machinery is already in place to do that.